Hello and welcome to our 15th session. In today's session we're going to be reviewing a little bit from Chapter 8, Depletion With. We're talking quite a bit about, and we'll just mention again non-rectifying ohmic structures. Then we'll go on to the last subject in Chapter 8, which is a discussion of the depletion capacitance. And finally, hopefully if we have time, we'll start on Chapter 9, which is the silicon metal semiconductor barrier, Schottky barrier, under external bias. But before we get started, we'll take a couple minutes to view a really wonderful flash mob performance of Ode to Joy. So we'll see you in about 4 minutes. Okay, so let's jump right into it. The first topic is the depletion width, W, in a rectifying metal semiconductor structure in equilibrium. Wow, that's a mouthful. equilibrium, no applied biases, nothing's moving, everything's static. It's rectifying. Rectifying means that we have a depletion width. There is a region at the silicon surface very close to the junction into the silicon, perhaps as much as a micron, which is depleted of mobile charges. The reason that it's depleted of mobile charges is because the Fermi levels of the metal and the silicon have to equilibrate. They have to become equal. And in order to do that, say for an N-type silicon, electrons must flow out of the silicon at the surface or near the surface into the metal. If it's P-type, holes flow out of the silicon into the metal, leaving it depleted of holes. What's in its place, however, for an N-type is ions that came from the doped atoms. For example, if it's N-type silicon, the doped atoms probably were phosphorus. They gave up an electron, they became positive. So we have a region of positive ions which are fixed close to the metal-silicon interface. Then we'll talk a little bit about non-rectifying metal-silicon structures. And here it's the exact opposite of the rectifying. Instead of the surface of the silicon becoming depleted of charge, there's actually more mobile charge. And then we'll talk a little bit about the depletion capacitance. Now, depletion capacitance is only valid for rectifying Schottky barriers, because in order to have a capacitance, we have to have a dielectric. The only place you have a dielectric is when you have a depletion region. And finally, hopefully we'll have time this time, we'll get into the new material in Chapter 9, which is non-equilibrium, where we power up the device and charge starts moving not only within the device, but actually moving in and out of the device. And we'll see what that does to everything, specifically the barriers in a rectifying metal silicon structure. Okay, so our basic equation is Poisson's equations, and a couple of things just to remind ourselves. Rho is the fixed charge density. In donor type, N-type silicon, it will be positive. It's measured in coulombs per cubic centimeter. Epsilon is the permittivity. V is the voltage, and that's the voltage that we measure with a voltmeter. And E is the electric field. Okay, just to reiterate, for an N-type material, the fixed charge density is equal to the donor density, assuming all donors are ionized, and it is positive. Now, last time we stated, without proof, we're going to prove it. The derivation is, I believe, in Chapter 9, check, but I'm pretty sure it is, that the depletion region width W is given by this expression here, and there are three basic components. There's the permittivity, there's the band bending, and there's the fixed ion charge density. So let's start with the let's start with the band bending. It makes sense that the bigger the band bending, the greater will be the depletion width. A little bit of band bending, for example, the band bending stops here, and then it becomes horizontal. We would have a small W, big, lots of band bending. The W, the depletion width, will be much larger. Again, this region colored in red is the region in which we have essentially no mobile charge or very little mobile charge. 10 to the 10th is considered very, very little. So that's intrinsic. And if it has 10 to the 10th or even close to the 10 to the 10th, that would be considered depleted of mobile charge. Okay, so why why is the expression for the depletion width have ND on the bottom? So it seems like the higher the doping, the smaller the W. That doesn't seem to be, at first glance, completely intuitively obvious. Well, I've tried to make that clear, or clearer, I guess you could say, with this little cartoon diagram. The first one on top is the case where we have heavy doping. Now, the critical issue in all of this is that in order for the Fermi levels to equilibrate between the metal and the silicon, there is a certain fixed amount of charge that has to be, again, we'll go for the N-type, fixed amount of electrons, mobile electrons, which are transferred from the silicon into the metal, independent of doping. Certain number of charges have to be transferred from the silicon into the metal. If it's heavily doped, those charges are transferred very close to the junction. This heavy line here represents the junction, and the electrons are the electrons that are sitting on the metal surface, right outside the surface. Of course, inside this metal, the electric field is 0. If, however, it's lightly doped, then I have to reach further into the silicon substrate in order to transfer that fixed amount of required charge from the silicon to the metal. And that's why here the depletion region width is small. I don't have to go very far to transfer the proper amount of electrons into the metal, whereas here with lightly doping, there aren't so many charges, fixed charges, close to the surface, so I have to go further and further in to the silicon, and that's why the W for lightly doping becomes much larger. Okay, so we got this guy and we got this guy, and now for the permittivity. Well, the permittivity, I've explained a little bit here, but the idea here is that, and let's actually go through this very quickly. If we're in this region between the minus and the plus, we can think of arrows going from plus to minus. That's the direction of electric field. It's negative, and as soon as we go to the right of this electron surface density, we cut maximum number of lines, and those number of lines continue until I get to the very end. And here, of course, I cut no lines, so here the electric field is 0, but the electric field is high because the closeness of the positive and the negative charge, whereas here I've got one arrow going from plus to minus here, but I've got another arrow going from plus to minus all the way over to the right. So if I'm in this region, I'm only cutting 4 lines, whereas here I think I'm cutting twice that number, and I don't cut this line until I go to the right of this charge. So here the electric field is small because I'm cutting less lines as I move from left to right. So large electric field is associated with small W's. Small electric field is associated with large W's. What makes the electric field small? Permittivity. Because we know that with high permittivity, the silicon atoms here will polarize themselves, plus charge moving to the left, and minus charge moving to the right, which reduces the electric field. And the smaller the electric field, the larger the W. So with a small epsilon, I have a larger electric field because I don't have that polarizing effect, and therefore I have a large W. With a high permittivity, I got lots of this little dipoles forming in the silicon, and since epsilon means a smaller electric field, small electric field means larger W's. Rather convoluted, but you get the idea. And I have a little bit of an explanation here in the text. Okay. Okay, so let's look at the permittivity in a little bit more detail. This is a table. Relative permittivity goes up as we go higher and higher. Okay, so for air or vacuum, the relative permittivity is 1. For SaO2, very hard, it's just hard to separate positive and negative charges in glass. Bonds are very tight. Most oxides have tight bonds, so the relative permittivity is 4. Most semiconductors have relative permittivities between 10 to 20. Silicon and gallium arsenide are identical at 12. Gallium arsenide is 16. I believe there may be one or two that have, I should say germanium is 16. There may be one or two semiconductors with somewhat higher, but I'm not familiar with them. And then we go to hafnium oxide, which is a rather interesting material, which has relative permittivity of 25, which kind of contradicts what I said about oxides, but there are some exceptions. This is one with a relatively high permittivity. And then barium strontium titanate, I believe is how you pronounce that, with a very high permittivity of 300. And metals, well, in metals, it is infinitely easy to polarize. So therefore, I say that metals have relative permittivity of 100, but that's with a question mark because we generally don't define permittivity for metals. Okay, so this is just a repeat of that figure which shows the silicon bulk or quasi-neutral or interior region with no fields at all, and the field in the depletion region. In this particular configuration, we have donors. These are positive, negative charges at the junction, so the field goes from positive to negative or right to left, and it is a negative field. Okay. This is just basically a statement of what we were saying before, that with heavy doping, we have a large electric field, a large slope of the electric field, and that would be this line right here. The electric field is negative, points from right to left, and it is maximum at the junction, which is right here. For lightly doped, we have a smaller electric field and a smaller slope. It is interesting, you might want to just note this, that the areas under this curve, this triangle, the area here is approximately equal to the area here, and the area is going to be proportional to the energy differences. And so that's something we'll take a look at a little bit more detail later on. Okay, so now I'd like to work with you something that's kind of interesting. I want to take a look at the units, and the units clearly on the left side are centimeters, distance. So I'm going to claim that the units on the right side, including the 1/2, raised to the power 1/2 square root sign, all units here all must come out to be centimeters also, or distance. All right, let's plow through it. Take a look at the first term on the denominator, Q and D. If it was just ND, it would be numbers per cubic centimeter. Q and D is coulombs, Q being electronic charge. So this term right here, Q1D is coulombs per cubic centimeter. Okay, now let's tackle the numerator. First term we come to is permittivity. Now, from the permittivity basic equation, Q equals C, not equal Q equals CV. I'm sorry. It's for a simple parallel plate capacitor. Parallel plate capacitor, the basic equation is the capacitance in farads is equal to the permittivity multiplied by the cross-sectional area divided by the distance between the electrodes. So obviously the cross-sectional area is centimeters squared, and the distance is the distance between the electrodes is in centimeters. So epsilon, the permittivity, is given by farads per centimeter. Okay, so that doesn't help us too much. We have to figure out what is a farad. Well, here we go a little bit, we use the other equation, Q equals CV, and we find that farad, 1 farad is a coulomb per volt. And a volt, bear with me right now, I'm going to claim that the units for voltage are joules per coulomb. We're going to show that later on. So let's accept that for right now and put that all into the equation up here. So we have that the permittivity is coulomb squared, there's coulombs on the bottom, flips up, becomes squared, divided by joule centimeter. The centimeter comes from here. So that's our basic unit for permittivity. And now we have the last thing is the band bending, and the band bending is in electron volts. Could be joules, that's the basic unit, but we measure it generally in the energy band diagram in electron volts. So putting that all together, the units are the units of permittivity, coulomb squared per joule coulomb, right here, this part, multiplied by the units for the band bending, which are joules, and divided by the denominator, which is coulombs per cubic centimeter. Of course, this cubic centimeter flips on top, and of course we take the square root, and one of the coulombs cancel out, so we still have a coulomb. The joules cancel out, and the centimeter cube cancels with centimeters, so I've got centimeters. Wow, that's not so good. I don't have centimeters. I have an extra term in here. Where do you think that comes from? Well, I'm going to claim that it comes because we used in this expression the band bending phi bi, but that is not consistent with Poisson's equation. Poisson's equation, there's no phi bi in here. There is voltage. So that's where the problem lies. And that gets us into this idea that we must have this guy measured not in joules or electron volts, but rather in joules per coulomb. So we really should have a V instead of a phi. And if we make that substitution, it's right here, joules per coulomb, then coulomb squared cancels with coulomb squared, and everything works out beautifully. So that is the problem, and whenever you see this expression, somebody is a little bit sloppy. Now, when it comes to sloppiness, I take a backseat to nobody. So I use it all the textbooks use it. You'll see it in lectures and all over the place. But it really is not 100% correct. We really should be using V rather than V. And I'm going to show, because I think it's so interesting and I think relatively important, that I'm going to show that the units of volts are joules per coulomb. And hopefully it'll be not too difficult. Okay, so the units of current on the right side, the units of current are just coulombs per second. R is a bit more tricky. The resistance R is equal to the resistivity multiplied by the length divided by the area. As the length goes up, you go through more and more and more distance, the resistance goes up. As the cross-sectional area goes up, the resistance goes down. Now the resistivity, I think this goes back to session 1 or 2, or probably session 2, is given by 1 over the number of charges per cubic centimeter multiplied by the electronic charge. Sometimes we use E, sometimes we use Q, doesn't matter, it's all the same thing. So this NE is measured in coulombs per cubic centimeter, and the units of mu, this is from chapter 7, is given by coulomb second per kilogram. I'll actually make a derivation of that in chapter 7, so you can check that out. I'm not going to derive it here because it would take a little bit too long. So the units of resistivity then are putting all that stuff in. This part here is the centimeter cube per coulomb. The mu is kilogram divided by coulomb second, because it's on the denominator, and we wind up with centimeter cubed kilogram coulomb squared second. So I put all that into I. This is I, coulomb per second. This is R, centimeter squared kilogram coulombs per second. Why did the centimeter cubed turn into centimeter squared? Because this expression here is 1 over centimeter. So I multiply the resistivity by a term which involves centimeters to the minus 1. So I cancel out one of these centimeters upstairs. And I get, what do I get? I get joules per coulomb. Coulomb cancels out here, so I get coulomb on the bottom. And what I have left over is kilograms per second squared. I should say kilograms centimeters squared per second squared. Centimeters per second squared is acceleration. Kilograms centimeters per second squared is force. Kilogram centimeters squared divided by second squared is energy. So all of this stuff here, everything here other than the coulomb, is in joules. So I get that I, or the units of I, are joules per coulombs, which obviously must be the units of voltage. And I find that the units of voltage are not joules, but joules per coulomb. And that is pesky, but it can be important at times. And finally, if we assume that the units of voltage are joules per coulombs, then we can write the product of the voltage times the current as voltage is joule per coulomb, current is coulombs per second, the coulombs cancel out, and I get joules per second, which is power. And of course we know VI is indeed power, and it's measured in energy per second. I don't go into any detail here, just basically qualitatively see what's going on here. These cases are not important. Non-rectifying metal silicon structures are not used in practice, to my knowledge. So what we have in the non-rectifying case is that the region between the metal and the interior, say half a micron or a micron or so, into the silicon becomes not depleted, but it becomes more full of mobile charges. So if it's N-type, there's more electrons close to the junction, and if it's P-type, there are more holes close to the junction. And it all depends on the difference between the metal and the silicon work function. So here we have a case, for example, of N-type, electron transfer from metal to silicon, not from silicon to metal, and the bands in this case go down. Now we always said that the band bending for N-type silicon goes up, and that's true, except for these two, or this particular one case, which is kind of pathological, in which the surface becomes more rich in electrons, and therefore the doping actually becomes higher. And for the P-type, it's exactly the opposite. The bands bend up in P-type in a non-rectifying Schottky structure, metals, silicon structure. Okay, so this is really now the start of the new material, and we're going to be taking a look at the depletion capacitance in a rectifying Schottky barrier junction. So the idea here is that because there is a region between the metallurgical junction and the interior of the silicon, which is depleted of charge, it is essentially a dielectric, and therefore it has a capacitance. And that is our next topic. Okay, so just to review again, I think reviews are good. There is a desire for electrons to flow from the silicon into the metal, driven by the fact that the Fermi levels are different. So as electrons go from the silicon into the metal, the Fermi level in the metal goes up, and we create a depletion region as an electric field. The electric field goes from right to left, which would push holes in that direction, but pushes electrons in the opposite direction. When the tendency for electrons to move from left to right due to the electric field balances the tendency for electrons to move from right to left due to the equilibration of the Fermi level. When both of those tendencies equilibrate or become equal, then the process stops, and the Fermi levels at that point are precisely congruent. That's basically what I'm saying here. There is a depletion region, and depletion region means that there are no electrons, but really it's not zero. It's about 10 to the 10th, but it's very high resistance, and it acts like a dielectric. For P-type silicon, exactly the opposite. The principles are the same, except that the bands bend down. Electrons go from the metal into the silicon. The Fermi level of the metal goes down when the tendency or the force pushing electrons from the metal into the silicon is balanced by the electric field, which pushes electrons from right to left. And both of those balance, then we have reached equilibrium. And the depletion region width from here to here, this is W right here, this width, and it is equal, same as W here. That is given by the expression which we took a fair amount of time to take a look at last time. We'll derive it in chapter 9. And let's get a little bit of a feel for the orders of magnitude here. The Q is 1.6 times 10 to the minus 19th, 1.6 times 10 to the minus 19th. N is anywhere from 10 to the 15th to 10 to the 18th. let's take it as, say, 10 to the 16th. So we're talking here somewhere on the order of 1 times 10 to the minus 8th. Epsilon, we will see, for silicon is 12. That includes epsilon 0, which is, I believe, 8.85 times 10 to the minus 14th times the relative permittivity of silicon, which is 12. So here we have 10 to the minus 12 divided by about 10 to the minus 4th, giving us 10 to the minus 8th. So VBI is about a volt, half a volt. So all of this stuff in the square root sign is about 10 to the minus 8th. We take the square root of that, we get 10 to the minus 4th. 10 to the minus 4th. What? Not meters, but centimeters. We always use centimeters in semiconductor devices. And 10 to the minus 4 centimeters is about 1 micron. There are 10 to the 4th, or 10,000 microns per centimeters. We know there's 10 to the 6th microns per meter. There's 10 to the 4th microns per centimeter. So W is on the order of 1 micron. And that makes a lot of sense. It can be anywhere from 0.1 micron to about 2 microns. Those are the normal ranges for the depletion region W. Okay, so this is a little bit of a preview. We're going to be looking at this quite a bit in the future for a bias junction, not an equilibrium. That's the whole subject for Chapter 9, but this again is just a preview. We have VBI turning into VBI minus some applied voltage. And let's just call it minus for now. And then we're going to take a look at what is the total amount of charge that is transferred. Now, if it's for an N-type silicon, again, this total amount of charge is electrons transferred from the silicon into the metal. Well, the total number would be equal to the amount of charge in the volume multiplied by the volume. And the volume, of course, is just the depletion region W multiplied by the area. Now, we're going to siphon off the area and say it doesn't appear here. So that's why everything is going to be with respect to cubic centimeters. But that's, again, a little bit in the future. So here we have not coulombs, but we rather have coulombs per square centimeter because we've taken out the area. And of course, N, the units of N, are coulombs per cubic centimeter. Multiply that by W, we get coulombs per square centimeter. So we basically put this guy into here, or something. We put W from 839 into here, and we get the following expression, which is relatively straightforward. There's a Qn, which cancels out this Qn, in fact brings a Qn on top. We bring it into the square root sign, so we get equation 841, which follows immediately. And I'm going to claim, and I think it's quite reasonable, that this is a capacitance. So we use our basic capacitance formula, Q equals CV, and this is what I'm looking for here. This is what I'm going to be concentrating on. What is the capacitance? Well, it's really not a normal capacitance. It's a capacitance whose width, W, varies. This is the distance between the electrodes. One electrode here, one electrode here. But if I vary the applied bias, that W is going to change. So this is a variable. It's not constant any longer in our capacitance formula. So it's really something like what we refer to as a varactor diode in circuit theory, but we're not going to take a look at that in any more detail, but it's a variable capacitor. And variable capacitors, instead of taking Q divided by V, we take the derivative dq dv. Now, this is not all that tricky. It's a little bit tricky in the fact that we're taking dq with respect to v sub a, which is buried in this larger formula. So how do we do it? We take down the 1/2. We first differentiate with respect to the entire structure in the parentheses, bringing down a 1/2 and bringing up a minus 1/2, which is what we have here. And then we differentiate the stuff in the parentheses, so we get 2qn epsilon. And that's where all this comes from. And the rest of it is just algebra. So basically this is just algebra here. That's not very difficult. And I get finally the expression for the capacitance is equal to qn epsilon divided by 2 VBI minus VA, all of it to the 1/2 power. Well, it's not terribly convenient here. So what I do is I square both sides. That gives me a linear relationship, but what I'm going to be plotting, this will be the independent variable, this will be the dependent variable. So it is convenient then to flip both sides to get the independent variable on top, which I do here. So I'm going to be plotting 1 over c squared as a function of VA, and this is what the structure looks like, and the plot is called a CV plot, capacitance voltage plot. There are 2 parameters of significance: the slope, which is given by or proportional to the doping, and the intercept, where VA is equal to VBI. So those will be the 2 important parameters that we get from the CV plot. So every CV plot is a straight line because it's 1 over c squared. That's a straight line with respect to VA. It has a slope which is proportional to the doping, and it has an intercept which is given when the applied bias is equal to the barrier potential or the barrier voltage. So those are really important things which I suck out of the capacitance voltage diagram. So let's stop here, and next time we'll be looking at chapter 9, which is beginning with at least n-type silicon under external bias. So that's going to be, I hope, quite interesting. And there's a lot to remember here. Sometimes I would ask the question, for example, the depletion width depends on the permittivity. How does it depend on the permittivity? Well, we know that as the permittivity goes up, the depletion width also goes up. But if somebody answers, and it's not unreasonable, that as the permittivity goes up, the depletion width goes down, which is wrong. But if you give a reasonable explanation for that, I wouldn't take off any credit. I would give that full credit. But that's just me. And we're going to hear a little song about that called The New Math. It's not the answer that counts, it's the principle. And we'll see you next time.
Some of you who have small children may have perhaps been put in the embarrassing position of being unable to do your child's arithmetic homework because of the current revolution in mathematics teaching known as the new math. So as a public service here tonight, I thought I would offer a brief lesson in the new math. Tonight we're going to cover subtraction. This is the first room I've worked for a while. It didn't have a blackboard, so we will have to make do with more primitive visual aids, as they say in the ed biz. Consider the following subtraction problem, which I will put up here. 342 minus 173. Now, remember how we used to do that. 3 from 2 is 9, carry the 1, and if you're under 35 or went to a private school, you say 7 from 3 is 6, but if you're over 35 and went to a public school, you say 8 from 4 is 6. And carry the 1, so we have 169. But in the new approach, as you know, the important thing is to understand what you're doing rather than to get the right answer. Here's how they do it now. You can't take 3 from 2. 2 is less than 3, so you look at the 4 in the tens place. Now that's really 4 tens, so you make it 3 tens, regroup, and you change a 10 to 10 ones, and you add them to the 2 and get 12, and you take away 3, that's 9. Is that clear? Now instead of 4 in the tens place, you've got 3 because you added 1, that is to say 10 to the 2, but you can't take 7 from 3, so you look in the hundreds place. From the 3 you then use 1 to make 10 ones, and you know why 4 plus minus 1 plus 10 is 14 minus 1, because addition is commutative, right? And so you got 13 tens, and you take away 7, and that leaves 5. Well, 6 actually, but the idea is the important thing. Now go back to the hundreds place. You're left with 2, and you take away 1 from 2, and that leaves... Everybody get 1? Not bad for the first day. Hooray for new math, new math. It won't do you a bit of good to review math. It's so simple, so very simple, that only a child can do it. Now that actually is not the answer that I had in mind, because the book that I got this problem out of wants you to do it in base 8. But don't panic. Base 8 is just like base 10, really, if you're missing 2 fingers. Shall we have a go at it? Hang on. You can't take 3 from 2. 2 is less than 3, so you look at the 4 in the 8's place. Now that's really 4 8s, so you make it 3 8s, regroup, and you change an 8 to 8 ones, and you add to the 2, and you get 1 2 base 8, which is 10 base 10, and you take away 3, that's 7. Okay? Now instead of 4 in the 8's place, you've got 3 because you added 1, that is to say 8, to the 2, but you can't take 7 from 3, so you look at the 64s. 64. How did 64 get into it? I hear you cry. Well, 64 is 8 squared, don't you see? Well, you ask a silly question, you get a silly answer. From the 3, you then use 1 to make 8 ones. You add those ones to the 3, and you get 1 3 base 8, or in other words, in base 10 you have 11, and you take away 7, and 7 from 11 is 4. Now go back to the 64s. You're left with 2, and you take away 1 from 2, and that leaves... Now let's not always see the same hands. 1, that's right. Whoever got 1 can stay after the show and clean the erasers. Hooray for new math, new math. It won't do you a bit of good to review math. It's so simple, so very simple, that only a child can do it. Come back tomorrow night. We're gonna do fractions.